Hi everyone. Welcome to week 2 of the Program Evaluation and Intervention Studies course. Today we're going to look at regression adjustment, linear and logistic regression. And today's meeting agenda for the first 5 minutes, we're going to identify the session objectives and discuss the importance of regression in assessing causal inference. And then for the first part of the discussion, we'll discuss standard linear and logistic regression and assumptions. And we'll review the benefits of relaxing assumptions, such as allowing interactions, and we'll introduce Cronbach's alpha. And the second half of our discussion, we'll look at regression case examples, and we'll demonstrate regression examples. We'll use the R package HAM, and we'll demonstrate how to improve model reliability and validity, highlight top coding and propensity scores, and rank variable importance. And then at the end, we'll wrap things up and outline our steps in preparation for the next session. Okay, so let's begin. We're going to review linear and logistic regression, and we'll start with our introduction and review. We have different motivations for multiple linear regression. First, there are two approaches in testing hypotheses or comparing groups. We either balance our sample on all important things and then test, or gather data on important things and balance mathematically to test. Number one is called an experiment, and number two, that approach is an observational study. Observational studies always work in healthcare. Experiments with randomization can be impractical or even unethical in healthcare. Randomization is a very powerful technique and great to use, but we don't always have that opportunity. Next, we see regression wasn't developed for research, but it was a natural fit. Regression allows us to simultaneously test relationships. Otherwise, we would need to do separate tests. And we have three reasons for doing regressions. The first two generally are concerns program evaluation. For our first reason, it's hypothesis testing. We expect the group that received the intervention will have a lower readmission rate, or we might say we expect the period after the vaccine to have a lower mortality rate, and so on. We have different hypotheses that resemble that. Our second reason is effect size estimation. We may want to know how much an effect has on an outcome. For example, what percentage of readmissions is reduced by an intervention, or what are the cost savings from an intervention program. And for our third reason for doing regression, it's for predict modeling. We create predicted scores for individuals to assign care. For example, we may try to predict a patient's chance of survival, length of stay, a child's lung capacity, and so on. But these are the three different reasons that we have for regression. The first two, we implement that quite a bit in program evaluations or intervention studies. And the third one, we're less concerned with that, but it's always a valid purpose for doing regression is for predictive modeling. And we have some identical assumptions between linear and logistic regression. They each have different assumptions. With linear regression or ordinary least squares regression, we have more assumptions, but here are three that overlap between linear and logistic regression. The first is linearity. For this assumption, we see that the relationships between the predictors and the outcomes variable is linear. This assumption can be relaxed with the use of nonlinear regression terms such as y equals a, which is our intercept, plus b, our predictor, and b squared. Using that squared term for that variable allows it to curve non-linearly. And our assumptions are things that we assume about how we're doing our analysis that that are required for us to say that we have valid results from our regressions. So for our second assumption, that is additivity. This is the impact of different covariance is additive, meaning that y equals a plus b1 plus b2. So we add the effect of each of our predictors into understanding our y or our outcome variable. So that additivity we see with the plus sign for a plus b1 plus b2. However, this assumption can be relaxed by using interactions. For example, our formula might be y equals a plus b1 times b2. So our two terms for b1 or variable 1 and variable 2, they interact because we're multiplying those two values together. And for our third assumption, we have the model specification assumption. The model is specified correctly. This is based on your own judgment. We want to make sure that we have all the variables that we find important in our model. And in this graph, we're looking at different trends that we might see in a regression. We have graphs for each. We have three different graphs, and each graph has a y-axis, which traditionally in regression or looking at data with purposes of seeing trends, we have on our y-axis we have our outcome, and our x-axis we have our predictors. We graph trend lines. The bottom left corner of that graph is where both x and y equals 0. So let's take a look at these different trends to see how we may interpret them. And we see on the top left, as mother's estriol levels increase, the baby birth weight increases. So as the estriol levels on the x-axis get larger, so do our babies, their birth weights increase. So we see what we consider a positive trend because the values are going upwards the further they get away from that bottom left 0, 0, those 0, 0 coordinates. As these values get higher, one value gets higher, so does the other. That's a positive trend. On the top right, we're looking at a negative trend. Our outcome is heart rate, and our predictor is age. As baby ages get older, their heart rates slow down, and so pediatric nurses will tell you that babies are born with faster heart rates, and as they age, their heart rates go down. So this is a negative trend. And at the bottom, we have a flat trend. So that would tell us that there's no association between our predictor and our outcome. Our outcome is birth weight, and our predictor is birthday. So maybe the day of the week, or which of the 365 days or 366, which of those days the baby's born on. Does that tell us anything about the birth weight? Based on these results, there's no relationship. There's a flat trend. It doesn't matter whatever the baby's birth date is, that birth weight is on average about the same as any of the other days. So these are the different types of trends we can see, and how we might graph these trends. That straight line, the straight lines that we're looking at would represent the trend line, while those dots represent actual data, and those lines are supposed to give us the best understanding about what those dotted lines mean. Okay, so now we're going to look at some background on our R-square and the area under the curve. We can tell how well the line fits the data with R-square for continuous outcomes. R-square is a measure of reliability or discrimination. It tells us how well our model is performing. AUC, or the C statistic for dichotomous outcomes, such as death or infections. We use R-square for continuous outcomes, and we use the area under the curve in logistic regression. R squared indicates the proportion of variance of the outcome accounted for by the predictors. In other words, it's the regression model reliability. The higher the R square and area under the curve, the more we can explain why values of Y differ, why our outcome values might differ. R square is the same value as the square of the Pearson correlation of a single predictor. Being able to estimate a predictor's effect while controlling for other predictors gives us a clear picture and more accurate results. But what does controlling for actually mean with regards to a linear formula? We often say this is the intervention effect controlling for age and gender. But what does it mean when we say control for? I'm going to get to that slide later, but I just want to mention that now because it's a type of interpretation that we often say, but I want to explain what that really means mathematically. Okay, so one area of interest could be health economic outcomes. These are a special case. They're not our traditional set of outcomes like maybe 30-day mortality, 30-day readmissions, catching an infection, CODIs, CLAPSIs, C. diff, or any other health-related outcome. Health economic outcomes are a separate class, but we often have but these are things we often come across, and they have special issues that we always have to pay special consideration for to analyze that data accurately. We often consider length of stay and cost. Those are things we often look at, and there's a strong relationship with length of stay and cost. The longer you're in the hospital, the more your costs are. Both outcomes are usually non-normally distributed, meaning they don't fit that bell curve. We have special cases of zero costs or positively skewed data because some patients have very high costs. So we may have a lot of patients that are on the low end for costs, and some might even have zero costs. But then we can have really high extreme values for some patients. They might be in the hospital for a full year or maybe even longer, and they accrue a high number of costs. And so costs can range from the very low end to the very high end, and that creates a situation with our data where it makes it difficult to analyze. Ways to work with that, we might consider the median as a good descriptor of the outcome. However, we are always interested in the mean from the economic perspective. We can identify high-cost patients or groups. So if we're working with maybe the finance department, they want to turn a cost savings into a business plan and analyze something that they call net present value, then we need to give them the average or the mean cost, even though we know it's comes from a positively skewed distribution where that mean, because of outliers, could look a lot higher than it actually is. Although we might have a low R-square that indicates a low explanatory ability for predicting hospitalization costs of individual patients, the model could still accurately estimate the anticipated mean hospitalization costs of groups such as children with the same characteristics. So when we have an R-square, we have different levels of R-square. A very high R-square, such as 0.80 and higher, can be used to provide individual predictions. But we often don't see that with intervention studies. What we usually see are kind of low to mid-level R-square values. If we wanted to make some sort of predictions from that type of study, we probably couldn't do it for individual patients, but we probably could be quite successful in using it for groups such as gender or a certain patient class, maybe patients treated for pneumonia or other groups. Okay, so we have a variety of different regression strategies that can help us in when we have difficult situations in our study or maybe our data collection, or if we generally just want to get the most accurate results as possible, we have some of these regression strategies that can help us. I have some of the variety of strategies that we can use, but these are generally helpful in most situations. First, we can use the literature and clinical expertise to create your models, so we can find out which predictors we should include in our regression model. And again, a regression model is based off a conceptual model. For example, if we're looking at predicting the chance of lung cancer, we would want to include a smoking history, tobacco use, their profession. If they work in coal mines, that's usually a strong predictor. If they've removed asbestos from buildings or houses in the past, that may contribute to lung cancer, and their medical history, their family history. But we would use our literature and clinical expertise to build our models. Our second note here is limiting the number of predictors to the most relevant will reduce something we call overfitting. And overfitting is model performance is overinflated due to chance because of too many predictors. And what we might get a great result in our current data, but we see that regression model performs poorly on future data because of overfitting. The results were a little bit too good to be true, and because we had too many predictors. And a good rule of thumb is for us to use less than 20 predictors. So using about 20, you probably want to use more than that, because we would open ourselves up to overfitting, meaning our results won't generalize over time. We're not going to see the same set of results in future studies. Another regression strategy is to relax our assumptions when relevant to get more accurate results. For example, we can have nonlinear effects. We can relax the assumption of linearity. We can relax the assumption of additivity by having interactions. Another strategy is data reduction. We can combine many similar variables into one variable. We can maybe, if we have 5 lab results, we can maybe combine that into one overall score. We can do that with factor analysis or principal components analysis. And we can also use imputation to help improve the accuracy of the results. Imputation is providing values or estimates when we have missing data. We're going to impute what that missing data could look like. One thing to keep in mind is interactions don't always replicate it in future work, so base it on theory or clinical relevance. And we can control for known risk adjusters like age, gender, health status, comorbidities, patient demographics, and attitudes. Those are always great risk adjusters in healthcare research. Okay, and so one thing we would like to do is keep our most important predictors. We may come across a situation where we have many stakeholders that believe that a certain set of variables are the ones that we should act on. And if you have many stakeholders, then you can have many different sides, each arguing for the what they consider the most important things to keep track of and to act on in the operational sense. And so what we can do is use these variable importance graphs to help answer that question of which are the most important predictors. A model with all clinically relevant predictors is better, but if a parsimonious model is desired that has the most power with the least number of predictors, we can determine the variable importance. We can rank predictors by standardized regression coefficients. Not all predictors are on the same scale, such as car weight and horsepower. So this helps to show which predictors have the biggest impact, regardless of what scale those values are on. So that's one option. Harrell's variable importance is a better option. It uses the F statistic from the ANOVA table. The larger the value, the more important, and we see that up top. We have 3 variables. The top one is DISP, engine displacement. The middle one is horsepower, and the third one is weight. And this is a model for predicting miles per gallon. So if we had to just focus on one thing, and then I would say weight has the most importance, meaning that the more we modify weight, the more change it has on our outcomes, such as miles per gallon. So if you only had to choose one variable to take some sort of action, it would be weight, this bottom variable. That's the most important. And using the AIC is another good option. The AIC is the IKK information criterion. The lower the value, the better. So that's another good option. And so now we're going to look at interactions. So an interaction is when the effect of a variable is dependent on the levels of another variable. To read more, see the Harrell photocopy. That's for chapter 2. But what an interaction is it's basically one variable's effect on the outcome is dependent on another variable. So if we're looking at age and gender, one area that we often see that is for the risk of heart disease. Women at younger ages tend to have a lower risk of heart disease, but as patients age, we see that their chances of heart disease are pretty close to men, and at some ages maybe even higher. It's also important to note that we just have more women alive at those older ages, so they catch up in terms of their trend, that men have a higher trend earlier on, and women have a lower trend, lower chances of heart disease. But as they get older, those two trend lines cross, or they touch at the latest ages. But that's an interaction. And here's a visual display of interactions. For interactions, it's in this graph we see it's the effect of car weight on miles per gallon is dependent on the type of transmission. So without an interaction term, or without an interaction period, then we'd see that the red and blue lines would be parallel. They're not parallel here; they cross in the first half on the left side of the graph. If there was no interaction, then we would expect to see that these two lines would have been parallel. The red line would not touch the blue line, and it would have an equal distance at the highest and lowest value on the x-axis. That's weight, and so that if there was no interaction, that red and blue line would not touch at all in this graph. However, I allowed an interaction. I multiplied the weight by the type of transmission, and that created an interaction term for me. And if there was no interaction, these two lines wouldn't touch, but they do. So what I did was I relaxed the additivity assumption, and that's perfectly okay to relax assumptions for interaction and linearity. And I relaxed the additivity assumption and allowed an interaction. I multiplied weight by type of transmission, and the interaction turned out to be significant and improves our model performance. So there is a benefit to doing it because it reflects the data more accurately. It reflects our understanding of our outcome and the association with weight and the type of transmission. So there's a benefit to doing that, a benefit to our model. We get more accurate results by doing this. And we see that lighter weight cars with manual transmissions begin with a higher MPG, but automatic transmissions generally have better MPGs over 3,500 pounds. And that's about where the middle of the x-axis is, about 3,500 pounds. Okay, so I'd quickly like to just review what scales are. These are scales that we look at, that we get through surveys, and they represent psychological dimensions, or they can represent behaviors or beliefs. So not only do they cover what we're thinking about, but also maybe things that we do on a routine basis. But we call them scales. They can represent from a low to a high range. Do I do this often or not at all? Or do I strongly agree with something, or do I strongly disagree with something? Scales are measured the level of behaviors or beliefs. Scales are often used in survey research. Common scales are 5-point Likert scales, like, for example, the ones we see where we're asked if we strongly agree or strongly disagree. But they can be cumulative checklists like Gutman scales. A common method for assessing Likert scales is the Cronbach's alpha, which is an extension of correlations. So we're seeing what the reliability is between these 5 different measures. If you use the HCAHPS results for anything, those are scales. They're asking about their experience with nurses or doctors, and there's a set of questions that measure your engagement with nurses or doctors. And we do multiple questions because often one question is not good enough. But if we have 5 questions and we have a very reliable set of questions, if they work well together, then that gives us greater confidence in using those set of questions to answer some sort of question on an outcome. So here's the standard set of Cronbach's alpha outcome, and this comes out of SPSS. In that top left corner, we see our Cronbach's alpha is 0.896, so it's about 0.9, so that's in the excellent range. We would have been happy with anything over 0.8, and we can use anything really over 0.7 or even a little bit lower if that's the best scale that we can develop. But usually anything above 0.90 is considered excellent, 0.80 is considered very good, 0.7 to 0.7 and 0.75 or higher can be considered good as well. Cronbach's alpha assesses reliability of multiple items in measuring the same dimension. Alpha ranges from 0 to 1. Common thresholds for a high, moderate, and low reliability are 0.8, 0.6, and low would be less than 0.60. To the left, we see that the alpha level is quite high, 0.90. This indicates that the 3 measures reliably measure our belief in data collection. Okay, so now we're going to look at our conceptual model of observed intervention impact. So I looked at data earlier where we showed that one graph where the 2 values interacted. Here's one of them that I have another one to show later, but so sometimes we might see results happen right away. Sometimes we might see our program or intervention impact happen later on. And so we might have different different examples of what success or program impact looks like. It may happen sooner, it could happen later, but we want to be aware that we have different types of impact, and that may ultimately affect how we do our analysis. So here are some examples of different types of impact. First off, we have optimal impact. The program or intervention has an immediate and continuous level of improvement. It's optimal because the early significant impact keeps on increasing over time. So not only do we see an impact right away, but we see continual impact from our program or our intervention. Next, we have immediate impact. The intervention has an immediate and sustained level of improvement. So we get our impact right away, but it may stay at a steady level. So it doesn't continue over time, but we do see impact right away. That maintains a sustained level. We can also see an incremental impact. The intervention has a moderate but continuous level of improvement. Next, we might see a mediated impact, and the intervention's improvement is not always immediately apparent and can be delayed. The intervention's level of impact is mediated by other factors such as the local site's expertise, motivation, and so on. Or the last option is that there is no impact. The intervention's impact is nil. The intervention group's trend remains steady and parallel to the control group's trend. So there's always a chance that if after we introduce an intervention or program, we might see that there's been no impact by the program at all. And so what we see is that for our intervention group, their success keeps going on at a level that we would have expected had there been no intervention at all. So let's take a look at what those kind of results can look like. So on the top left, we have the example of an optimal impact. We see in the blue dashed line that represents our treated group, our intervention group, or our program group. And then that orange vertical line represents the treatment period. That pink horizontal line represents the control group. So we can see how the control group performs. And we have a dashed gray horizontal line as well. That represents what we call the counterfactual. It's the hypothetical if the intervention group was untreated. So this could show what could have happened if there was no intervention. So for our first example, for the optimal impact, we see that when the intervention began, which is where that orange vertical line is at, we see an immediate increase. That blue dashed line goes up, and then we see it continuously improve over time. So that's an optimal impact. We see an immediate impact, and we see it continually improve. So on the top right, we have our immediate impact, and again we see the intervention start. Our blue dash line representing our treatment or our intervention group, we see that increase, and we see that that level of improvement is sustained. It doesn't continuously improve, but it also doesn't get worse. So we see that there is an immediate impact and followed by sustained improvement. And so on the bottom left, we have what's called an incremental impact. So that would indicate that the increment was small. But we do see that it may not be significant, but we do see that it continues. We see improvement continue, and then we see it within a certain time frame that we do have a significant difference. So there is an improvement. It just takes longer. And then for that fourth outcome, we see, for that fourth type of impact, we have mediated impact. So we may see that the intervention doesn't show an improvement right away, but that could be because of other reasons. The impact is mediated by another factor, and that could be that we may start our staff. They may use a new practice after the intervention starts, and maybe not until maybe partway through the study, we might see that, okay, at that point, that's when our patients start to get involved in that interaction, or I'm sorry, not that interaction, but in that process. So maybe in the beginning, we just start our staff off with new learnings or new practices, and then later on they start to provide that care for our patients. So we don't see the impact right away. It may come later. For the optimal impact, I've seen that happen more when our outcome is some sort of process, like maybe gathering labs. You can see an immediate impact on those type of outcomes where it's a process outcome, and we can continually see that improvement as well. It's hard. I think it's harder to see it for like true health outcomes like mortality, definitely readmissions or infections. We may not see that continual growth, right? Just because those things are just harder to move. It's harder to move those types of outcomes with things that are like process outcomes. It may be just easier to move, so you can kind of see this great type of growth. And so somewhere in between those very tough health outcomes that are difficult to move to some of our easier outcomes, we can see these different levels of improvement. Okay, so now we're going to get into linear and logistic regression. And we're going to begin with cost and a 30-day mortality. We'll cover what are considered propensity scores. The propensity score, that's the conditional probability exposure to treatment given the observed covariates. In other words, a propensity score is the probability of being selected into the intervention group. For example, hospitals in greater need of interventions may have patients at greater risk that are older, male or female, etc. The propensity score gives a probability for all patients of being in the intervention group and helps rule out those variables as causes of the intervention success. Propensity scores can be used for matching patients or just used as one extra variable in the model. And we call that propensity score covariate adjustment. This is especially helpful if we need to use many variables to create propensity scores. And top coding, that's a practice that transforms the highest value to a threshold value. For example, we might have a patient cost of $75,000, but we've top coded at $50,000, meaning that $75,000 cost is now converted to a $50,000 cost. In regression, outliers can have an undue influence in our results. Cost and length of stay often have very positively skewed outcomes, and we benefit from top coding because it lessens the effect of outliers. We can get more accurate coefficient results in R-squared by top coding. In other words, these results might hold up better or be more generalizable when we top code our outcomes. Top coding is an easier process compared to alternative methods such as log normal transformations, alternative regression styles, etc. If we top code, it gives you great results and it's easier to implement. And here's more of a description in the Ayatsoni PDF. And so top coding is very helpful in these situations, and this is what I was describing earlier as a positively skewed cost outcome. So we call it positively skewed data because we have a tail that goes out on the right side. If it went out on the left side, it would be negatively skewed data, but we see that tail drags out on the right side. That's what outliers look like, and that makes using regressions tricky because those outliers can make our results look, can inflate our results and make our intervention effect look better than it actually is. So our first example, we have a 30-day cost. We have a hospital introduces a program to help reduce 30-day costs for inpatient stays. We begin with a commonly used approach, a t-test that compares pre-intervention and post-intervention cost savings and find that it's over $2,500. We then improve our model by adding in different research design elements to give us more accurate results. That t-test is what we would see up top. We have observation 1 followed by a treatment, and our observation 2, which is our post-test. We can improve that by adding in a control group, which we see in that bottom table 5.1. We see that observation, treatment, observation, but we see on the bottom that's our control group. Okay, so here's our actual data. There's an intervention effect that seems to be more incremental or mediated. The effect seems to happen a few months after the intervention began. Our blue line is the intervention group, our pink line is our control group, and that vertical green line represents when the intervention started. It started at 5 months and was modified. You can think of it as an intervention plus at the 9th month. So we do definitely see signs of an interaction. So we want to allow for that in our analysis and create an interaction term. And so in this table, I'm looking at 6 different models. We begin with just by looking at cost predicted by program, and we see that cost saving is $690. For the other models, I'm going to look at the cost saving at the 12th month, which is at the end of this graph. That's a difference just on raw data. It's a difference between a little over 13,000 compared to a little under 8,000. So $690 doesn't seem to quite match what we're seeing in the data. I add in the month variable because we've talked to our staff and they say the real impact's going to happen later on. We believe it's the progress to be more incremental. But even then we see that saving is $689. So we go ahead and use that interaction, and there's a big change. We see that cost saving looks more like $5,900. And we see that on the next column over we have our R-square, and it's jumped up dramatically from 0.01 to 0.19. So there's definitely an improvement by adding that interaction. It now reflects more of what we're seeing in the data, and most importantly, it reflects our conceptual model based on our discussions with our clients. So then we add in other predictors that we know are important, such as age, female, gender, and risk. And so that now we get a lower cost estimate, but we do get a much more accurate result, and we see that in our R-square. And then we add in top coding. So we top code our cost outcome because we know we have outliers. We use the same model as before, and we see that estimate dropped from 5,700 to 5,300, but we also get more accurate results. The R-square jumped up to 0.26. I did add in a propensity score at the end, and I only used 3 variables in that, so maybe it didn't give me the most impact. I would continuously use propensity scores whenever possible, but in this model the cost jumped up a little bit and the R-square jumped down. So in the end, I'm going to use this model that I have highlighted in yellow because it gives me the best results in terms of accuracy, and that cost level is about over $500 less than Model 2, but when we return our estimates to our finance department, say this program treats 10,000 patients, so that difference of $500, well, if we have 10,000 patients, then we would estimate that we're $5 million more accurate, because it's about the difference between Model 2 and Model 4 is about $500. So we would save our hospital system about $5 million in maybe wasted funds, but also if our program is seen as is $5 million less effective, then it could be a bad review of our hospital program. So we might be setting our hospital program up for failure if we don't give the best estimate. So we did cop code at $17,150, and we see probably Model 4 is the best one to go with. Here's the outcome of what it looks like. I highlighted in green program month and MP. So when we multiply these three values, that's how we get our estimate. Because it's an interaction, we need to use all three together to see what the impact is. And here's ham code. You can see on the bottom I have I top coded at 17,150. I add this argument, says propensity, and I use these three predictors: age, female, and risk. Here's variable importance. Again, if we have multiple stakeholders and they each have different ideas of how we should act to improve our program, we can highlight what's the best thing. And we see that MP, which is the interaction between our month and our program, is our most important predictor. So how we can interpret that is that what we would probably want to do is quickly and safely enroll our patients into this program. And I'm saying quickly because month is part of that interaction, so we know timing is important here. So we've covered the areas. We often say, what is controlling, adjusting, or balancing for? It means we use the average for each predictor, except our three interactions in this example terms, to calculate the Q predictor's effect. For example, the predicted values for the first and 12th months for the intervention and control groups are, so on these top two rows, it's for the intervention group. For the intervention group at 1, what we see in red, we actually modify those values. Say in that first one, it's month 1. In that next row down, we see MP equals 12. That's the 12th month. But we control for age, female, and risk by using those same values, which would, in this case, the mean. We can use the median as well. But when I'm calculating the effect of our program, I'm controlling for age equals 62. And you'll see in each of these examples, age equals 62. So that's what we actually mean by controlling for age. And female, there's 49% female. Risk is about 0.50. So when we calculate the effect of our intervention program, we're holding these values constant. They're each going to be 62 in our example. So it's a kind of the term, it's a little vague, but this is what it actually means mathematically. And so we can then calculate these graphs that show the trends, the trend lines. And then here's our logistic regression example. I actually do have in my different files, I have multiple linear regression and logistic regression. So I'm just going to show that we have a similar situation with this data where there's an interaction between terms. And when we do that interaction between month and program, that turns out to be our most significant variable. I'd recommend, if you wanted to review more on logistic regression, to check out my files in my past courses I've taught on that, and then there's going to be a lot more information in there. Here's Cronbach's alpha through ham. I'm using the alpha command, and it prints up some of that similar data we get. For this, this is a different set of questions, but for these 5 questions, there's a 0.919 or 0.92 Cronbach's alpha level, and we see that we have something called scale statistics of if item deleted. If we drop that first question, it'll improve our alpha by 0.930. It's a little bit better, and it's already at the excellent level. So you can technically improve your alpha and get a more reliable scale, but that question number 1 may be really important to you, so you may want to keep it regardless of that improved alpha. And I use this all with my ham package. In this slide, there's information of where it is on R. Here's my GitHub page where it has current information. You can click on this link, that third line, and try it out ham on your own. And here's some my next version will probably be out in late December, and I'll make some improvements there and add some things, and then I have some example code. And here's in the appendix is something on model validation, and that can tell you about calibration and discrimination. This is more important when you're doing predictive modeling, but it's a key part of that, so I wanted to include that. Thank you, everyone.